Okay, hello everyone. So this week we're going to begin with lecture slide 11, focused on Poisson's equation and work function. Afterwards, we're gonna begin with uh, better semiconductor context. So with some more details. So the chapters corresponding to this content is chapter 5 and 14. Okay, so metal semiconductor context stuff. Some more details are introduced and described in the book chapter 14. So don't forget to read all the sentences in chapter 5 and 14. So in the second slide, you're gonna see some brief introduction what the Poisson's equation is. So let's suppose that we have a very small infinitesimal volume, and the left hand side, left edge is defined as x of 0, and the right edge is defined as x0 plus delta x. So the distance between two surfaces, I mean the left hand side and right hand side surfaces, is delta x. So very small width this cube has. And the cross-sectional area is defined as area A. And now the electric field, yes, the electric field is electric field at x of 0, or just at an arbitrary x. The electric field intensity E of x is defined like that. And the electric field is now getting into toward the infinitesimal volume, and the other notation denoted as electric field at x plus delta x. Okay, so I guess instead of 0, you can say that arbitrary position at x, and left hand side is corresponding to position x, and right hand side is corresponding to the x plus delta x. Okay, so the electric field intensity at the right hand side surface is defined as electric field E of x plus delta x. So certain variation has been occurred while the electric field uh, has been going through this infinitesimal volume. So the question is, why the electric field intensity has been varied while it is going through this infinitesimal small volume of cube? The answer can be found from the fact that there exists a certain amount of charge within a small cube. So if the charge density denoted as rho in the unit of Coulomb per cubic centimeter, then if as long as this rho is non-zero, the electric field intensity before and after getting into this small cube should be changed. So how changed? The answer can be found, and that physical event can be explained with Gauss's law. So as you have learned in undergraduate class, electromagnetics, in Korean 전자기학, you may have a chance to hear and learn the details on Gauss's law. Well, herein, let me briefly review what the Gauss's law is. So now let's talk about the one-dimensional space only. In other words, the electric field is directed along the plus x direction or minus x direction. Okay, so one-dimensional space is given, and for a given one-dimensional space, the electric field can be formed along the plus x direction or minus x direction. That's it. No other options. The vertically directed electric field cannot be considered in this one-dimensional space. Then now, the electric field variation, as shown in here, right? The electric field final value minus electric field value at initial stage or initial place, and final, the position at final, and the position at initial. So that is corresponding to the delta x and delta E, right? And that can be written as dE dx if I'm using a differential form. Okay, and in this specific case, the electric field at final means here at x plus dx delta x, the electric field intensity is corresponding to the electric field at final, and the electric field intensity at initial stage, initial position, is corresponding to the electric field at x. Okay, and the final position is x plus dx, delta x, and initial place is x. So those two x's should be cancelled out. So we're gonna get delta x and ex plus delta x minus ex. So you can see that equation on the left hand side. So this electric field intensity variation divided by for a given x value or variation along the x direction can be rewritten as dE dx as shown in here. All right. Then the Gauss's law said this electric field intensity variation with respect to x is very proportional to what? Yes, how much charge has been stored within this unit small volume. Okay, so dE dx is proportional to the charge density. Then what is the coefficient for this relation? Yes, it is defined as dielectric constant. So this material has a certain amount of dielectric constant. We can complete and build up this equation. That is denoted, that is written here. So dE dx is equal to what? Yes, charge density divided by dielectric constant. But herein, I'm going to use a silicon or semiconductor here. In S indicates a semiconductor. Okay. So now you have you have caught your own intuition and idea how to write up the equation for Gauss's law. Okay, and this equation has been named as Poisson's equation. So basically, Poisson's equation is developed to describe how the electric field intensity has been varied along the x direction. And that is that variation of electric field intensity is very associated with charge density for a given volume. And that relationship can explicitly explained with Gauss's law. Therefore, Poisson's equation is almost identical to the Gauss's law. Okay, so if you want to write up a certain form of equation to explain Gauss's law, always think of Poisson's equation for Gauss explaining Gauss's law. Okay, if I have extend out the from one-dimensional space toward three-dimensional space, then this equation form should be modified to this. Okay, so electric field intensity should be described and expressed with a vector, and this del indicates the differentiation value of this vector. Okay, so herein I don't want to go into some more details on the three-dimensional vector analysis. I guess you have a chance to learn some details on vector analysis in calculus class as well as in electromagnetic class. So herein, to make our life much easier, I'm going to use a one-dimensional analysis even for Gauss's law. So dE dx, how much electric field intensity has been varied, is very proportional to the electric field charge density divided by dielectric constant. Okay, So please remember this Poisson's equation for further analysis for p-n junction diode as well as metal semiconductor contact, MS contact. All right. So now let's assume that dopant atoms, impurity atoms, are fully ionized. Previously, as we have learned, all the dopant atoms at room temperature are fully ionized. Well, if I go back to the Fermi function or Fermi energy, stuff, you may guess and estimate quantitatively how much dopant atoms are ionized at room temperature. Well, if you remember a certain specific example for asking those questions, actually dopant atoms are ionized not fully, but about 98.3%. In other words, 1.7% of dopant atoms cannot be ionized at room temperature. Okay, but anyhow, just to make our life much easier, let's assume that all the dopant atoms are completely ionized. Then, now let's write down an equation for charge density in the Poisson's equation. So in the previous slide, we have learned this Poisson's equation, and now this charge density, I mean this small cube, suppose that this is a silicon material, then we're gonna put some dopant atoms, right? Donors and acceptors, as well as it has its own electron concentration and hole concentration, right? So let's make us some close relation and write up an equation how to close charge density with this value, donor acceptor concentration, electron hole concentration. So the answer can be found here. The charge density in silicon material can be written with four components: hole concentration, electron concentration, donors concentration, and acceptors concentration. So since donor itself themselves are donating its own, fifth electron to the silicon material, so it's going to be positively ionized. Okay, so plus. What about the acceptor? So acceptors are, accepting the free electrons from the silicon material so that it is going to be negatively ionized. So minus, right? And what about the hole? Hole is, as I told you, the positively charged particle and carriers to flow current in silicon. So P is plus. And what about the N? Electron concentration, indicating electron concentration. This N electron is negatively charged particle carrier in silicon. So I have used the minus sign. But if you think about the unit for P, N, ND, and Na, all unit is number of carriers divided by cubic centimeter. So for given unit volume, how many carriers are there? Or how many positive carriers, how many negative charged carriers, how many positive ion, particles, impurities, how many negatively charged acceptors are there. But here the unit for charge density is coulomb per cubic centimeter. So to match the unit on the left hand side with the right hand side, we should multiply something. So what is this? Yes, coulomb per number. Then this number unit would be cancelled out, and in the end, the coulomb per cubic centimeter. So therefore, we need to find out this guy. What is this guy? Which has a unit of coulomb per number of carriers. Yes, unit charge. Okay. So unit charge, denoted as a small q, has been multiplied in this equation. So in the Poisson's equation, the identity of this rho has been rebuilt as q times p minus n plus nd minus na. If acceptor has not been included in your own silicon sample, then you can just plug in zero value in this term. Okay, all right. Then now let's move on to the next one, work function. I guess in general physics class you have learned the definition of work function. What is it? Yes, the work function is defined as the energy required to take out a single electron away from the material. Again, work function is defined as the energy required to remove single electron out of the material that you have. Okay, but the more precise definition said that the minimum required energy to take out a single electron from the material. Okay, so I said minimum. So going back to the energy band diagram for matter, you can draw your own energy band diagram for matter. So matter has no band gap energy. So energy states are, almost continuously existed. No band gap energy, but uh, you know, between two different energy states are very discrete. However, it looks like there is no band gap. But in semiconductor has its own band gap energy, as illustrated here. EC minus EV indicates the band gap energy. Okay. So you're familiar with this band diagram for silicon material, right? Just a two solid line, solid color, two parallel line indicates, band edges, EC and EV. That's it, right? But here in this slide, we would like to indicate which energy difference is corresponding to the work function. So going back to the definition for work function, I said the work function is the minimum required energy to take out a single electron away from the material. So in case of matter, uh, the energy states are almost continuously distributed out, and free electrons are now sitting and filling out the empty energy state. And in the end, all the free electrons in this matter has been used and to take out, no, no, to fill out all the empty energy state. So this energy level corresponding to the Fermi energy level indicates what? Yeah, below Fermi energy level, all the energy states are filled with electrons, but above Fermi energy level, all the energy states are empty. Okay, so in other words, above EF, the probability of finding an electron is nothing, zero. But below Fermi energy level, the probability of finding electron is 100%, 0 or 1. So this energy level, in other words, Fermi energy level, at this Fermi energy level, the probability of finding electron at this edge of Fermi energy level is 50%. If the energy level is very slightly above EFM, the probability value of finding an electron is 0, but the energy level slightly below the Fermi energy level, it is almost 100%, 1. So therefore, at the very energy state corresponding to the Fermi energy level, the probability value of finding an electron is, yes, 50% or 0.5. Okay. Therefore, going back to the definition for work function, the minimum required energy to take single electron away from this matter system can be defined as this from here to here. So what is this, by the way? Yes, E naught indicates a for Q energy level as described here. So for Q energy level means if the any electron in this metal, this electron is actually bonded or included in this metal. But once this electron has been excited up a lot, and in the end, it's going to fill out this E naught energy level. In other words, this electron has received very much amount of energy, then it is excited up to this energy state corresponding to vacuum energy level. Then we can claim that this electron in matter is not anymore existing within the matter. It is freed out. Okay, so it becomes a free electron and very away from the matter material. So in other words, we can say that we have take out the electron from the matter. So the but question is the minimally required energy to take out an electron from the matter is defined as work function. So in this energy band diagram, the minimum energy to take out a single electron away from this matter can be defined as this: E naught minus what? Yes, this energy level, EF matter. Okay, EF matter. So suppose that we have a single electron sitting at this Fermi energy level, then how much energy is necessary to take out this electron away from the matter? Yes, E naught minus EFM, right? But this energy is minimally required to take out a single electron away from the matter. We can take out electron uh, existing at this energy state, but we need this energy difference. Okay, so this energy difference is much higher than E naught minus EFM. But we have defined that work function is defined as the energy minimally required to take out a single electron away from the matter. Okay, so now phi m matter work function is defined as what? E naught minus EF metal. Okay, so similarly, we can adopt the same definition for work function for semiconductor. So phi s, semiconductor work function denoted as phi s, is defined as E naught minus EF semiconductor. Okay, so whenever we are talking about the work function in the field of electron device, always think of this value, E naught minus EF. Okay, all right. So up until now, we have gone over uh, all the details for basic, solid state physics. From now on, we're going to begin with uh, matter semiconductor context first. Afterwards, we are going to study p-n junction. Okay, I guess we have 5 more weeks left behind. So I guess I may not uh, cover all the details for p-n junction diode. So if you take my class next semester, semiconductor device engineering, 반도체 소자공학 in Korean, then you're gonna learn some more, maybe AC characteristic and transient response of p-n junction diode. I guess I can finish and cover up to DC characteristic of p-n junction diode, I guess. Okay, so please review uh, some some all the basic parts before moving forward to understand MS contact and p-n junction diode. So I guess this slide is really, you know, give us the flag uh, by this slide. We have covered up all the basics and uh, introductory parts for solid state physics. And after this slide, we are gonna start to learn some more details on uh, electronic components such as MS diode, metal semiconductor diode, and PN junction diode. Okay, so I guess it's a good timing to have a short break time here, and please have your own time to review all the lecture notes and again go back to your textbook and try to refresh your memory with uh, all the lecture slides and chapters of textbook. Okay, so please go ahead and let's see you in the next movie clip. Okay, bye bye.